Hello everyone, this is Professor Kuehn. Today I'll be continuing my discussion of the law of the lever. This is from a student's guide, volume 2, chapter 6, and the reference is day 2 of Galileo's Dialogues Concerning Two New Sciences. You might remember that at the end of my previous lecture, I simply stated what the law of the lever is. So let me restate that. I'm going to use the same words that Galileo uses. It's a bit of a mouthful, but I think you'll see that it makes sense. Then what I'll do is I will briefly state it, kind of translate it into a mathematical form. And then instead of just trying to memorize the formula, we're going to try to see where this formula comes from. Okay, so what is the law of the lever? And here Galileo is talking about like a bar. You might think of a bar resting on a fulcrum or perhaps a teeter-totter. Okay, you're probably familiar with the teeter-totter where you put two people, one on each end, and if they're just the right distances and just the right weights, then they can balance each other. The teeter-totter will balance. So here it is. For a bar on a fulcrum, he says, the force bears to the resistance the inverse ratio of the distances which separate the fulcrum from the force and the resistance. Okay, so again, the force bears to the resistance the inverse ratio of the distances which separate the fulcrum from the force and the resistance. Okay, so what does that mean? Let's draw a picture and then write this down in a mathematical form just so we understand what he's saying. He's saying if you have this point right here is called the fulcrum. It's the point on which this lever or bar balances. And what he's saying is if the fulcrum is not right at the center of it. Now we're going to ignore the weight of this bar and just imagine that it's a very, very light bar compared to the weights you put on it. Okay? So let's suppose you apply a force to this end. Maybe a person sits on this end, or you put a block or something on this end, and you put another block or a weight or something on this end. And so you have a downward force on this end. And it is at a distance from here to here. We'll call it the length of the length that the force is being applied from the fulcrum. And in order to balance that, you need to apply a resistance force over here. He calls it the resistance. I'll call that R over here. And that is going to be applied a distance L, we'll call it L sub R, from the fulcrum. Okay, so you got these two forces, and they're potentially different forces, and they're potentially different lengths. And those are going to be in equilibrium. So he says that these will be in equilibrium, or the entire lever will be in equilibrium. It'll be static. That means it won't be moving. It won't have a tendency to go down one way or the other. If the force bears to the resistance, that is the ratio of these two, in the inverse ratio of their distances from the fulcrum. That means the force is to the resistance in the inverse ratio, that is as the ratio of the length to the resistive force to the length of the original force. Okay, so this is what he's claiming. So this is the claim of Galileo. This is his claim for them to be in equilibrium. Okay, so I've kind of translated his language, his text language, into a mathematical formula. Okay, so the force bears to the resistance in the inverse ratio of the lengths as the lengths of the resistance and the force. Sometimes you'll see this written in a slightly different way. If you're comfortable, which most of us are, with algebra, we can rearrange this, cross multiply it, and you'll sometimes see the law of the lever written as the force times this L sub F equals the resistance times L sub R. And sometimes in different textbooks you'll see this with F1 times L1 equals F2 times L2. And I guess this is just another way to write that same formula. Galileo does not state it like this, again, because he has a tendency to write things as ratios, so you're always comparing like quantities. Notice the left-hand side here, you're relating forces. On the right-hand side, you're equating lengths. Here, we're more cavalier about it. We're multiplying a force by a length. Galileo would be uncomfortable with this kind of thing, but generally speaking, we tend to be more comfortable about this sort of thing. Okay, if we write it like this, and actually I'm going to write it in a little bit more general way, F1 times L1 equals F2 times L2. Sometimes you'll see it this way, where force 1 is the force applied to one side, L1 is the distance from the fulcrum, F2 is the force applied to the other side, and L2 is the distance of that force to the fulcrum. So sometimes you'll see it written this way. These are all equivalent statements. Okay, and maybe I'll point this out right away. If you think of this quantity, the force times the length, this has a name, and it is called the torque. We'll call this torque 1, or maybe we'll call it the moment number 1. It's a tendency. It's a force times a distance, and it's a force that tends to rotate something about some point. Okay, so this is the torque that this force is applying, or the moment being applied by that force. And this side over here is the torque that's being applied to this side, torque 2 or moment 2. So you might think of, if this is force 1 and this is force 2, this torque, that force times that distance, is trying to rotate this around in the clockwise direction. And this, if this was force 2 and this was length 2, this torque, force 2 times length 2, would try to rotate this around in the counterclockwise direction. And so the law of the lever is also, you can say that the torque in one direction is equal to the torque in the other direction, or the moment in one direction is equal to the moment in the other direction. Okay, later on Galileo is going to talk about moments, or tendencies to twist something about a point. Okay, so kind of from here on, we are doing a little bit more modern notation. This is the way Galileo is thinking about it for the time being. Okay, now what I've done so far is I simply stated what the law of the lever is, what Galileo's claim is, but notice we have not proven this. All we've stated is this is what Galileo says. And I never like to just memorize formulas because you don't really know what the limitations of the formula are, how it comes about, if there are any alternative ideas that might be better. So how do we know the law of the lever is correct? And is it correct? How do we know if this is correct, if it's a true formula? Well, there are two ways to approach this. I'll give two answers. The first answer is one could do this empirically or experimentally to limited precision. We could do this experimentally. You could go into your laboratory and set up a fulcrum and a ruler or something like that and apply different forces to the sides and measure how long the lever arms have to be in order for them to balance, and take enough data that you're convinced that this is approximately correct. Of course, this will give you an approximate, tell you whether or not this is approximately right. This is an approximation, since it's experimental. And experiments only give you approximate results, of course, always. The other way, and this is the way Galileo does it, he does it deductively. He says you don't need to even go into the laboratory. This is interesting because we think of Galileo as kind of a hard-nosed experimentalist who's interested mostly in observation as a scientific method. But he says, no, you can prove this strictly deductively. That is, we could prove this to be true mathematically starting from a self-evident axiom. We could simply deduce this or prove this mathematically or geometrically, mathematically / geometrically, beginning with a single self-evident axiom. That's what an axiom is. It's either something we all take to be true or we all consider to be obviously true. A single self-evident axiom. If you accept this one axiom, which he argues we all should, then you can simply deduce the law of the lever geometrically. And that is what we are going to do here. And he says, by the way, in the course of these dialogues, remember this is a discussion between Segredo, Simplicio, and Salviati. They're discussing this, and one of them, I don't remember, it might have been Simplicio, who said, yes, Aristotle knew about the law of the lever, and he's right. But Salviati goes on to say that it was Archimedes who first gave a geometrical demonstration of the law of the lever. Archimedes was also an ancient Greek philosopher, and he tended to be more mathematical than Aristotle was. So anyhow, what we're going to do is, I think I'm probably going to run out of time. So I'll just reiterate here is that this is an Archimedean proof that Galileo recites. Okay, and we are going to talk about this in my next lecture.